Reducing measured distances. When we reduce measured distances, we can essentially break the process up into 3 steps. The steps must be done in this particular order as well. So the first step is to deal with the slope distance. This is the actual distance we measure from our EDM, electromagnetic distance measuring equipment, to the prism, and this is actually measuring or reducing the slope distance. Some of the things that we have to contend with slope distance reduction with EDM are the instrument constants. Generally these are zeroed in the instruments, but from time to time instrument constants can have a place in the reduction, particularly when we want to go for high precision, where we must take careful account of our various reductions. Now, our atmospheric reductions, we must allow for various changes in the atmosphere. As a ray travels through the air or the atmosphere, there are various layers and things that can affect the distance measured. Generally we would measure temperature, pressure and humidity. Then once we get to the other end, of course, there is the prism constant, that various prisms have different constants that are added or subtracted from measurements to get a true slope distance. We must also just hark back to previous years where we have particularly where we use the long steel band. And using the long steel band, of course, there are the additional concerns or things that we must allow for, and that is the sag of the band, or the catenary that is created when a band is tensioned up to the correct tension. And we can also make allowances if we do not tension the band correctly but over tension it or under tension it. There are various corrections that can be made to ensure that we get the correct slope distance. Now once we've got the slope distance, we then move on to reducing the slope distance to a horizontal distance. And to do this, essentially there are 2 corrections. One is for the slope itself, which is just a straight trigonometrical relationship between the slope angle and the slope distance, reducing that to the horizontal. But we must also allow for curvature and refraction, the curvature of the earth and the tendency for light to bend down towards the earth in refraction, thereby affecting a zenith distance or slope angle that needs to be adjusted for that refraction. So we reduce our slope distance to the horizontal. Having got our slope distance to the horizontal, this is the horizontal at where we're measuring. So if we're measuring quite a high distance or a high height above sea level in New Zealand, say perhaps around Taupo or in the North Island and some of the higher areas of central Otago where we can be quite high above sea level, we thus must obviously make what's called the sea level correction, although generally with the ellipsoid closely approximating sea level we could be forgiven for reducing this to and creating an ellipsoid distance. The other thing that we must allow for is a scale correction. We live on a curved earth. However, we try to represent our plans and maps and things on a projection onto a flat piece of paper, and this enables us to, with various projections, to get a variety of different answers. The most common one in New Zealand being the projection we use being the transverse Mercator projection, where bearings and angles are held and do not change generally, as it is a conformal projection. However, distances and that do have scale applied to them, and so the projection distances may be different to the actual true distance or ellipsoid distance. Now, in general run-of-the-mill measurement or linear measurement, when we work from day to day, we sort of work in a world that's a perfect world, where generally the temperature is 20 degrees and the pressure is a very constant. And this is generally the case, and because of this and various other factors, particularly if we say are in and around the Waikato and areas like that where we work generally at 50 metres or less above sea level, that we don't have to worry about a lot of these slope reduction adjustments, because generally we can just measure straight out of our machine and be within a reasonable sort of accuracy. However, attention to detail is what we need to achieve higher accuracy. So if we are in particular circumstances required to measure distances at a very high accuracy, one of the things that we can do that with the general equipment that we use is to apply our corrections more carefully and more thoroughly and more methodically, rather than just take what we get from the machine. However, there may be circumstances where the standard gear that we use, generally in the survey field, is just not up to it in terms of the brief for the job or whatever, and then we need to go to more accurate equipment, and the next level up from our standard EDMs and theodolites that we use, next level up would be the precision distance meter, and then for very highly accurate work we could go to the high precision distance meter. So it should be noted that generally on a day-to-day basis, the gear that we use, there are two levels of accuracy above that, and that our general stuff that we use, sort of in the order of plus or minus 5 mils to 1 centimetre, generally does the work or meets our requirements most of the time. Reducing the slope distance. Instruments constants. One of the things we do quite regularly with our gear is we calibrate our gear. In other words, we measure known distances with our gear, and then we work out constants and what have you that we need to apply to those measured distances, so that we can make sure that when we measure other distances we get the correct answer. This is called calibration. In other words, there are various constants and things that we can apply to a measurement to make sure that it is calibrated against a standard. We also have in the machine various things such as index error and things like that. Now, these errors or these constants or adjustments are generally zeroed in every instrument at the time of purchase, and at each time that we send them in for servicing, the service people will calibrate the instrument to make sure that the correct settings are in the instrument, so that when we get a distance out of the instrument, it is calibrated against the standard. From time to time we need to verify that our instruments are reading correctly. In other words, that we put them over a known distance, we get the right answer. And for this to occur, the right index constants and calibration constants need to be in the machine. We can of course check these ourselves and have a look at them, but my advice is to leave that to the service people, to the experts, rather than doing it yourself maybe once in every 6 to 12 months. It's far better to have someone who does it on a daily basis, and thereby ensuring that you have got an expert doing it who is a practiced expert. So these instrument constants, although they exist, generally don't show up to us, and we check them by ensuring that our instruments are serviced regularly, and that from time to time we do checks to make sure that they haven't gone out of calibration. Atmospheric corrections are usually on a day-to-day basis. We just set them to the average for the area. They only need closer attention when we were looking at high accuracy work. And modern total stations have the ability to measure a number of these atmospheric things such as temperature, pressure and humidity. But if we want to do very accurate work with the gear that we use, which we've established is probably has 2 further orders above it, then we would need to at least look at trying to get accurate temperature and pressure and humidity readings so that we can adjust our measurements. Probably also would involve, at the higher accuracy, a different methodology of measurement, in that we would possibly set all of the temperature, pressure and humidity to 0, so that when we could use our measurements to apply with the formulas, rather than having the machine apply the formulas inside the software that's involved. Also, we possibly would need to look at how we measure these things by perhaps as a minimum measuring temperature and pressure and humidity at each end of the line rather than just at the line that we're measuring at. Prism constants can be a source of error. Myself, I have available a number of different prisms that I use for various reasons and types of prism, and the prism constants range from 0, -30, -34.4, -69, -11 to +10, and there are others. It is very important with the machine that you have the correct prism constant dialed in. As you could see there, if you had a -69 constant in when you should have a +10, that's a whole 79 millimeters of possible error. It is very important, therefore, that you check that you have the correct prism constant. There are other ways around doing this. One of the ways is to ensure that you only have or use prisms with one constant, so that there is no fear of changing and then not changing back to the correct prism constant at the appropriate time. You must therefore exercise care when using different and or a mixture of prism types, because this can lead to confusion and error. Again, I just must make mention of the long steel band. The long steel band was used in the past, seldom used today, but there are additional reductions that are required for reducing the slope distance of a long steel band, and these relate to sag, the catenary calculations for the sag, and the tension that the sag has been applied to the band. So if we use our band at the correct temperature, obviously we just have a sag correction, but we can do a further calculation if we apply the wrong tension to the band, which enables us to adjust for too much tension or too little tension. Although I have to say, this is not a calculation that I have ever had to use myself. In all the measurement that I've done with the long steel band, we've always applied a 7 kg tension and just used standard sag tables for the band in question. Reducing to the horizontal. Reducing the slope distance to the horizontal involves 2 interrelated activities. In the first instance, we usually measure the zenith angle, which enables us to determine the slope angle, although we can use the zenith angle directly to determine the horizontal distance. This is a straight trigonometrical relationship that we should be reasonably familiar with and be able to work out. The formulas and what have you for these things are all included in the textbooks and notes and quite easily found. However, coupled with the slope distance reduction is the curvature and refraction correction. Now, in the diagram on the right, we will see that if we were at point A and we observe a straight line, we can see that we will be observing along this purple line here generally, and that if we pull that back to the center of the earth, but because we are actually want to observe or measure the curved distance there is a little difference that we have to make in here, which will affect our measurement. This is the curvature, or what we have to allow for in the curvature. Of course, that will affect the zenith angle that we measure. So generally our curvature can be applied in a number of relationships. It's related to both the horizontal distance and the zenith angle. But also factored into that is the refraction correction as well, because when we observe from observe our vertical angles, there's a tendency for the light to be curved down towards the earth, and this is the refraction correction here, which I have shown. You will note that they are in opposite directions, and that the curvature refraction is the curvature correction is in the opposite direction to the refraction correction, and by and large the largest correction is in fact the curvature correction, and so the two are usually combined in a fairly standard equations that are applied. They can either, as I've said, be applied to the zenith angle to allow for the curvature, or it can be applied as a function of the distance, as that can be seen that we usually mathematically represent the curvature correction by a standardized equation which maps the curvature of the earth based on a fixed radius, or the radius of the particular projection that we're using. So we reduce our slope distance to the horizontal at the height of measurement by just our straight trigonometrical reduction and applying our curvature and refraction correction. Having reduced our slope distance to the horizontal, but at the height that we are observing, which I've represented here with the yellow line, we now have to reduce our measured horizontal distance to sea level, because in our cadastral system and most of our mapping systems we represent things as if they were at sea level. Now clearly, if they are at 200 or 300 meters above sea level, these distances, measured distances, are going to be slightly longer than if they were measured at sea level, and this is for map projections. And I emphasize here that this is for map projections. If you are doing perhaps an engineering project at a height of 300 or 400 meters above sea level, then the actual distances that you measure there for that projection should perhaps be used. And you need to consider this. Should you be applying sea level correction for the job or for the purposes of what your client wants? But just for cadastral purposes in New Zealand and for mapping purposes, all our distances are horizontal and at sea level. So we apply this sea level correction, and the formula for that again are fairly widely published and reasonably easy to follow, and the detail is not going to be discussed here. Now, having produced our measured horizontal distance now to a sea level, we now must apply what we call a projection correction, because although we've reduced our distances A to B to the sea level or ellipsoid, they're sort of interchangeable. They are different but generally coincide to the sea level or ellipsoid. We now want to represent our distance on a projection, and our projection is generally a flat sheet of paper. So here we are where we've projected these A and B to the projected distances A dash and B dash. Now, over short distances there possibly won't be too much involved, but where these distances get quite long, the projection distance becomes quite a factor. And what happens is, in our normal situation here in New Zealand, is that in our Travis sheet we enter our projection bearings and our ellipsoid distances, and then from those, using our software, we end up with projection coordinates. However, the calculation of the projection is done within the software. However, if we are to take the coordinates of A dash and B dash and work out the distance between them using our standard calculator or coordinate geometry type things, we will not get the ellipsoid distance between A and B in some cases, because there is a scale factor involved. Now, in New Zealand we have 13 meridional circuits. We use a transverse Mercator projection, and the parameters of that are fairly widely available. Now, in 11 of the 13 meridional circuits we have a central meridian, and the scale factor on the central meridian is 1, and this is represented by this diagram here, and this is in 11 of the 13 meridional circuits. This is represented east-west, so we have a transverse Mercator map projection, and so our central meridian is going north-south, and this would be west over here and east over here. So our scale factor is dependent, or what the parameters or the variables that determine our scale factor are the easting element of the coordinates. However, in 2 of our meridional circuits, Mount Eden and North Tyree, we have a slightly different situation. Because of their large extents east-west, these particular meridional circuits have a different scale factor on the central meridian. In the case of Mount Eden, the central meridian scale factor is 0.9999, which in effect means that at some point to the west and some point to the east there is a scale factor of 1 on a meridian parallel to the central meridian. The effect of this is not to have as large a scale factor out at the extents of the meridional circuit. Part of the reason for the meridional circuits was to keep the projection or the scale factors smaller, and this is what determines the area of the circuits themselves. But in the case of these 2 circuits, it was decided to have a central meridian scale factor less than 1, which enabled the scale to be better distributed, or more evenly distributed, at a smaller magnitude over the east-west extents of the projection. So there you have it, is all of the corrections and what have you that are applied to a measured distance to get it to a point where we can use it either on a map or in a particular situation. But the thing to remember through all this is the projection you are using appropriate? Why would you be, if you are measuring for a kilometre long bridge at a height of 400 or 500 metres above sea level, why would you be applying a sea level correction, and why on earth would you be applying a projection correction to that? Because you may well find yourself in some great difficulty with things not fitting together. So it's very important that you, one, understand what projection you are using, what effect that projection has on your data, and what effect that projection has on your project and how you're going to apply your project and whether it is fit for the purpose. But in measuring distances, there's a lot of things to consider, and you need to get it right, because if things don't fit, it's fairly obvious who's to blame.